Okay, do you have any questions? Now, you missed that we were discussing how to write the volume charge density of various distributions, various charge distribution using the Dirac deltas and the step function. Now, I will do one more example on that. So if you have questions, you can ask. And the others, do you have any questions on the examples that we had done? Let's do one more example. Let's assume we have a rod of length L and total charge Q. Let me also choose my coordinate axis. What is the density of charge density? One point to pay attention to is this is the volume charge density. So we should be able to write down the volume charge density corresponding to a given charge distribution. Okay, so where are these zeros? It is equal to 0 if z is larger than L over 2 or z is less than minus L over 2. X is non-zero, y is non-zero. Okay, so at all of these points, our volume charge density should be 0. So that basically tells me that the volume charge density should be proportional to Dirac delta of x, because it should be 0 at all values of x except in a single point. Dirac delta of y, and again, it should be 0 everywhere except in a single point. It's a single value of y. And then we should have this step function, L over 2 minus z, because it should be 0 if z is larger than L over 2. And we should also have a step function, L over 2 plus z, because it should be 0 if z is less than minus L over 2. So if there are these Dirac deltas and step functions, then at least the zeros match. And then, of course, we have to multiply this with some function of x, y, or z. We are using the Cartesian coordinates in this example. This example we will do using the spherical coordinates also, after we do this Cartesian coordinate example. Well, the Dirac delta already tells me that I should put x equal to 0 everywhere. So that function f doesn't really have an x dependence. So this is in fact equal to f of 0, 0, and z. Dirac delta x, Dirac delta y, theta of L over 2 minus z, theta of L over 2 plus z. So that function over there is actually a function of z only. And that will basically tell me how the charge is distributed over this rod. I mean, is it uniformly distributed? Is there more charge towards the ends? Or the charges are concentrated towards the center? We don't know. I mean, we should be given that information. If we are told that the charge is uniformly distributed, this basically tells me that f is a constant. Let's again call that A. It's just the name we give. So for this uniformly charged rod of length L, the charge density is A times Dirac delta of x, Dirac delta of y, theta of L over 2 minus z, and theta of L over 2 plus z. Now we need to calculate this A, and for that we will use the information that we have the total charge is equal to Q. This is equal to A times integrals over x, y, and z from minus infinity to infinity of Dirac delta x, Dirac delta y, theta of L over 2 minus z, theta of L over 2 plus z. Well, the Dirac delta will make the x and y integration trivial, so we can take the x and y, just everywhere we should put x is equal to 0, y is equal to 0. And the step functions tells me that although the z integral, we are integrating over the whole of space, the only contribution comes from z is equal to minus L over 2 up to z is equal to plus L over 2. So this is equal to a times z. So the A just turns out to be A times L, sorry. Q over L, so here is our charge density. In Cartesian coordinates. Well, let's do the same in spherical coordinates. This time it is r, theta, and phi. So in terms of r, theta, and phi, rho of r, theta, and phi is equal to 0 if r is larger than L over 2. Pi over 2. Theta is not equal to 0 or theta is not equal to pi. Theta equal to 0 is the upper portion, theta is equal to pi is the lower portion. So we can say that rho r, theta, and phi, this is equal to, well, we have theta of L over 2 minus r, because if r is larger than L over 2, it is definitely 0. We have the Dirac delta of theta. This is theta is equal to 0. Or, well, this, I mean, if there is one part that has proportional to this step function and the Dirac delta, let's call its coefficient f1, r, theta, and phi. And again, we have this time the Dirac delta of theta minus pi. F1 basically tells me how the charge is distributed in the upper portion, and F2 tells me how the charge is distributed in the lower portion. Again, we can say that, okay, let's assume it's uniformly distributed. Which basically tells me that F1 and F2, they are both constants. They don't really depend on, well, they don't depend on R or phi. Well, in fact, they cannot even depend on phi. Because theta is equal to 0 and theta is equal to pi over 2, their phi is not really well defined. And this Dirac delta of theta just tells me that theta also has a fixed value. They can only depend on r. And if the charge is uniformly distributed, they don't even have that r dependence. So rho of r, theta, and phi is equal to a times theta L over 2 minus R times Dirac delta of theta plus Dirac delta of theta minus pi. I will make one mistake, and then I will wait for you to find it. Well, let's determine A. We have Q is equal to A rho times dV. This is equal to rho is, okay, dV is dr r squared from 0 to infinity, d phi from 0 to 2 pi, d theta from 0 to pi times sine theta times a theta of L over 2 minus r times the Dirac delta of theta plus Dirac delta of theta minus pi. Well, there is one point that you should pay attention to now. You see, the Dirac deltas are 0 at the boundaries. So in fact, when we were defining the Dirac delta, we said that if you are integrating over the region in which, over the point at which the Dirac delta is 0 from one side to the other side, then the Dirac delta has the value 1. So here we are not going from one side to the other side. We are actually right at the point of the Dirac delta, where the Dirac delta is 0, is on our boundary. But I will assume that basically it's just close, I mean, both the Dirac deltas are in our region. So effectively you can say that I'm not really taking this rod exactly at the z-axis. I'm tilting it slightly and taking the limit that this angle goes to 0. In that case, that ambiguity is removed. Well, then our integral doesn't really go from 0 to infinity, but that step function tells me that it goes from 0 to L over 2. And if I integrate over R, that just gives me L over 2 cubed times 1/3. Question? Okay. Phi integral just gives me 2 pi. And then theta integral just gives me, I have two Dirac deltas. One gives me sine of 0, the other one gives me sine of pi. Sine of 0 is 1. Sine of pi is minus 1. So 1 plus minus 1. This is equal to 0. Oops. So what is A?
Step function is not correct.
Why not?
Because both have the same step function.
So
Sine of 0 is not 1.
sine of 0, sine of, yeah, both are 0. Okay. Sine of pi is also 0.
In both cases, it's 0.
Yeah. No, it is sine in the volume element. The dV in spherical coordinates is r squared dr d cosine theta, if you like, d phi.
What if you take sine outside the integral?
How can I do that? It's inside the integral. It depends on the integration. I didn't take it out. I used the Dirac deltas. I made a mistake somewhere.
The Dirac delta, as I remember, for spherical coordinates is different.
Yeah, that is why I put the A. You know, that Corfi constant A. Well, the mistake is somewhere starting from here down at some step.
And the both are same.
Hmm?
Why the both step functions are same?
Yes, there should be a minus element.
Why?
The size.
R should go from 0 to L over 2. R is a positive number. It cannot go to minus L over 2. We are in spherical coordinates, or the radial coordinate is always positive.
A may magnitude.
Hmm?
A may magnitude.
Okay, A might depend on theta. But eventually we are setting theta is equal to 0 or pi, no?
Can we take step function instead of direct delta?
Well, the step function gives me a range of non-zero values. But we have a 0 everywhere except then a single point.
Those two different theta.
Hmm?
You have two different thetas, one for the step function and one for angle.
Okay. Okay. But I mean, I'm not planning to change that, unfortunately. Step function is also denoted by theta, just like the spherical angle theta. There is nothing much to do about that. If theta has an argument, it's the step function. If it doesn't have an argument, it's the angle. Go down. Where?
Before sin theta.
Here. Why?
Because sin theta is minus.
Well, not really. I mean, you also need to change the limits. Exchange the limits, that brings an additional minus sign. So what does uniform charge distribution mean? I said that, okay, the charge distribution in uniform, and hence F1 is equal to F2, which is equal to some constant. Is it true? How can we test it? What does a uniform charge distribution would imply? Del Q over del R? Not necessarily. Let's see. Well, let's see. We have this rho of R. Let's consider some very small volume over here on the z-axis. Okay? So rho of R times dV, this should be constant. That's what uniform charge distribution basically implies. Whether I take this volume over here or over here, as long as I am inside my rod, let's say, on the z-axis in my rod, it should be constant. It shouldn't change as I move away. So what does this imply? Rho of R, well, we said that rho of R is F1, I'm not writing the arguments of F1, times theta of L over 2 minus R, Dirac delta of theta, plus F2, theta of L over 2 minus R, times Dirac delta of theta minus pi over 2. Well, dV is r squared dr d phi times d theta times sine of theta. Do you agree? Well, of course, we are integrating over a very small range of the, well, we are inside our rod. So the step functions are 1. Well, this volume covers all values of phi. So the phi will bring me a factor of 2 pi. So F1 sine theta Dirac delta theta plus F2 sine theta Dirac delta of theta minus pi over 2 times r squared dr, no, d theta should be equal to constant, not 0. Well, so this basically tells me that F1 should be equal to A over r squared sine theta, and F2 should be equal to A over r squared sine theta in spherical coordinates. Well, this is kind of problematic. You see, theta is 0 in F1 and it is pi over 2 in F2. In both cases, sine of 0. We are dividing by sine of 0.
Cancel.
Yeah, it cancels. Formally, you can still write this down, but it's kind of problematic because of this Dirac deltas. It does cancel. So rho of r is actually A over r squared sine of theta, theta of L over 2 minus r, delta theta plus delta theta minus pi over 2. Well, Dirac delta theta over sine theta is kind of singular in when theta is equal to 0, but so is the volume element. When theta is equal to 0, it is singular, it is 0. So both singularity kind of cancel each other. How do we determine A? Well, again, back to this argument, rho of r dV, this should be equal to Q. This is equal to A. Now let me integrate over dr from 0 to L over 2. Integration over phi will give me 2 pi. Integral over the theta from 0 to 2 pi. And r squared and sine theta, they have canceled with the volume measure. We are left with delta theta plus delta theta minus pi over 2. Theta integral brings 2. This is equal to 4 pi L over 2. 2 pi L times A. So A is equal to 1 over 2 pi L. Q over 2 pi L. And rho of r would be Q over L, 1 over 2 pi r squared sine theta Well, I wouldn't use the spherical coordinates for this density of charge density. But if you insist on using this, would be the form. Now, we know how to write the charge densities. Let's calculate some electric fields. Once we know the charge densities, we can evaluate the electric fields. Well, this is the electric field. This is the charge density that I will be using. Well, once you identify your volume charge density, calculating of the electric field is just doing some integrations. The electric field is equal to dV rho of r prime, r minus r prime divided by r minus r prime cube. This is always true. The electric field at the point r, in terms of the charge density, it's always can be written in this form. Let's write the volume elements, dx, dy, dz, all from minus infinity to plus infinity. Q over L, Dirac delta of x, Dirac delta of y, theta of L over 2 minus z, theta of L over 2 plus z, r minus r prime divided by r minus r prime cube. Well, the Dirac delta x times Dirac delta y kind of makes it trivial to evaluate the x and y integral. This is equal to q over L. It just tells me that wherever I see an x and y, I should put some 0 over x prime, sorry. These are x prime, y prime, and z prime. Wherever I see x prime and y prime, I should just put 0 there. And the step function tell me that the z integral is from minus L over 2 to plus L over 2, not from minus infinity to plus infinity. Times r minus r prime divided by r minus r prime cube. Now we need to evaluate this integral, but first let's express everything in terms of, this is z prime. Everything in terms of x, y, z, and z prime. Now, r vector is equal to x in the x direction plus y in the y direction plus z in the z direction. Similarly, for r prime vector, it's x prime in the x direction, but we said that x prime is 0. Y prime in the y direction, similarly, we said that y prime is 0. The only thing is the z prime coordinate. This is equal to z prime in the z direction. This is r prime. Essentially, r prime is the position of the charge that is creating the electric field, and we are calculating the electric field at the position of r. So r minus r prime, this is equal to x in the x direction plus y in the y direction plus z minus z prime in the z direction. And its magnitude is x squared plus y squared plus z minus z prime squared square root. So you just put them back. Is the electric field at the position r was q over L from minus L over 2 to L over 2 dz prime. Well, r minus r prime vector, let's write the coefficients for it. 1 over x squared plus y squared plus z minus z prime squared to the power 3/2 times x in the x hat plus y in the y hat plus z minus z prime in the z hat direction. This is our electric field. So its components, the x component will be q over L times x minus L over 2 up to L over 2 dz prime 1 over x squared plus y squared plus z minus z prime squared to the 3/2. The y component is Q over L Z Y, the same integral no, there's no y, x squared plus y squared plus z minus z prime squared to the power 3/2. And the z component will be Q over L from minus L over 2 up to L over 2 dz prime z minus z prime divided by x squared plus y squared plus z minus z prime squared to the power 3/2. Well, the z component will be the easiest to evaluate because the integrand is a complete derivative. Anyway, in principle, you can just evaluate all the components. But for such a simple charge distribution, most of the time this is not what we will do. We will not be writing down the charge density and evaluating the integral. I mean, this is a problem that you could solve with your knowledge in general physics, first year physics course. But the idea here is mainly, okay, this looks more complicated to evaluate, just writing the charge density and using the integral of the electric field. But no matter what your charge distribution is, no matter how complicated it is, once you identify the charge, volume charge density, the rest is straightforward. The complication does not change as your charge distribution changes. Whether you have a simple charge distribution or a more complicated charge distribution, the steps will be identical, more or less. But the tricks that you would be using in the first year, they would work in simple cases, but not in complicated cases. Questions? We don't really have that much time to discuss one more problem, so for today I will just end it over here. Next week, the lectures also, you will be bringing your questions. You will be uploading your questions first on the Hour2 class. I will arrange a place for you to upload your questions, your pre-reports. And for the recitation also, I would rather if you bring questions that we can solve in detail. But in the lecture hours, we will be mainly discussing the conceptual things. In the recitation hours, we will be doing the examples, specific concrete examples. And in all of them, you will be bringing the topics to be discussed. You will be bringing the questions to be solved.
Can we pre-report templates?
Well, just empty page. That's the template.
Thank you.
Okay, pre-report, I repeat. I mean, the idea is to make sure that you have read the reading part and also you have thought about questions. I mean, if you don't write questions, I don't accept your pre-reports. So that when we come to the class, if nobody wants to voice their question aloud, I will just pick up the pre-reports and read the questions from there. So everybody will be asking questions. Pre-reports, okay, the lectures, I will not keep lecturing throughout the semester. The problem is basically it doesn't work. I mean, you just come listen passively, and at the end of the day, you don't really learn, you just forget it. So this is the concept called the flipped classroom. You do the learning. I don't do the teaching, but you do the learning. So what we will be doing is I will be giving you reading assignments. You will read them. And then you will write what you didn't understand. You will have your questions, and you will ask those questions to your friends, not even me. The priority will be your friends should be answering them if they understood it. So it's important that you should come here already having understood at least some of it. Maybe not everything, but some of it. So the part that he doesn't understand, probably you will understand, so you will be able to explain to him. So you will be discussing and teaching each other, and I will be supervising. And of course, I mean, if there is a point that none of you could really understand, in that case, I will be explaining.
So a report is simply questions.
A pre-report is just 1 page long, where you have ideally half a page, or typical half a page should be what you understood, because one of the problems is also sometimes you think that you understand something, but you understood it wrong. So I should also make sure that you understand it correctly if you don't ask it over here. So half a page what you understood, half a page your questions. So finding questions, in order to find questions, you would have to think about the material.
So you don't upload.
You will upload them. It will take time, don't leave it to the last minute. So coming up questions is not that easy, and you are not so used to coming up with questions. So that is one thing which I hope you will be able to improve throughout this semester.
Will you do this weekly or every week?
Yes.
Or every week?
Well,
Every class,
for every, yes.
not weekly.
No, I mean, I want you to prepare, I will be giving you a weekly pre-report, reading assignment. For the weekend, I will tell you that, okay, you should read this and these sections in the book and prepare a pre-report. You should study the book. For example, those students who have taken my freshman from me, they are used to preparing these pre-reports. But the difference of this pre-report was in first year, I didn't really require you to understand the material on your own. This year, you are supposed to understand the material on your own, work on it on your own. You have the weekend for that. And during the lecture hours, probably the first hour, I will be just going over the material without too much detail or rigor. I will just go over the topics and just mention some of the topics which you shouldn't miss. So we will be discussing those topics definitely. And in the rest of the hours, you will be asking questions to each other and answering each other's questions.
Which other book?
Greiner. The book is Greiner. I mean, I'm uploading these slides on Hour2 class also. Once you register, you will be able to see the lecture notes on Hour2 class. The book is Greiner. It's classical electrodynamics. Complete your add drops as soon as possible, so you will be able to have access to the material in Hour2 class.
We exclude the mathematical expressions from our pre-reports.
I would rather if you do. I mean, most of the pre-reports quite often come with lots of mathematical formulas. That's not what I want. And all the formulas have their stories. You should be telling me the stories. What did you understand? What does those formulas that you saw in the book tell you? I would be the happiest teacher if you would not write a single formula. But I would say that's the real physics. I mean, once we write, let's say, these expressions, or even this one, once you write this one, let the computer do it. Why should we be spending time on how to evaluate this integral? I mean, the computers are great for such repetitive routine jobs. Let them do it. But what do you understand from this formula? That's what we should be discussing. Or for any other formula in the book. Okay? So see you on Friday, the latest.